slightly unreactive metal into an acid, then we feel that no reaction is taking place because we don't see bubbles, we don't see many bubbles, we just see a tiny hint of bubbles in the vessel, in the test tube. So we conclude that, oh, there is no reaction, this is unreactive. But the thing is that it's not true that it is unreactive. It is reacting slowly. Like the breakdown of hydrogen peroxide is very slow, and it may seem like it's happening, it is not happening. It is so slow that we feel like it is not taking place. However, the case is that the reaction is taking place, but it is slow. So the reaction can be feasible, but it might be very slow. But if it's very slow, it doesn't mean it is not feasible. It still means that it is happening. So a reaction may be fast or it may be slow, but it is feasible, which means that it is happening. So there is no measure of feasibility. Feasibility just means if a reaction is happening or it is not happening. It can be slow, it can be fast, but it is happening. That's what matters. And if it's not happening, then we don't care if it's slow or fast, because that won't only happen. We will see no reaction. There will be no slow reaction, there will be no fast reaction, there will be no slow reaction. So no matter how fast or slow a reaction is, it is feasible because it is happening. So we have done this chapter. It is a fairly small chapter. So let's just do some exercises involving Gibbs free energy changes and standard entropy changes. So So the table shows 4 reactions. For each reaction, predict the sign of the entropy change, delta S naught. If you predict no entropy change, write no change in the table below. The first one has been done for you. So what we have to do is these 3 which are after the first one. So this is magnesium solid. Remember the state symbols. Magnesium solid plus half O2 gas gives me magnesium oxide solid. Now there can be 2 approaches to this question. One is that the total number of moles on the reactant side is, is 1.5. The other is, so there are 1.5 moles on the reactant side and there is 1 mole on the product side. So as the number of moles is decreasing from reactants to products, disorder is decreasing. So the entropy change is negative because the disorder is decreasing. The other approach is there is a gas in the reactant side, but there is no gas on the product side. And since a gas is being consumed, we know that entropy has to decrease because gases are more disordered. So if a gas is being consumed, then the disorder is decreasing and the order is increasing. So the entropy change has to be negative. So these are the 2 approaches to this question, to this particular reaction. The second reaction, calcium sulfate solid plus 5H2O liquid gives me hydrated calcium sulfate, which is CaSO4.5H2O, a solid. So in total we have 6 moles on the left hand side, which is the reactant side, and we have 1 mole on the product side. So since the number of moles are decreasing from reactants to products, the disorder is decreasing and hence the entropy is decreasing. So the entropy change will be negative because the entropy is decreasing. Now last reaction, NaHCO3 solid plus H plus aqueous gives Na plus aqueous plus CO2 gas plus H2O liquid. Again, 2 approaches to this question. We have 2 moles on the reactant side because 1 of each, and we have 3 moles on the product side because we have 1 of each and 3 products. So the number of moles has increased, which means disorder has increased. So entropy change will be positive because the disorder has increased. So the entropy will increase. But the second approach is that in the reactant side there is no gas, there is only a solid and an aqueous solution. and in the product side there is a gas. So in the product side, as there is a gas, we know that gases are the most disordered.